So hello everyone. So this is the last segment and continuation of volumetric analysis after equivalent weight and n factor. So titration is very important in chemistry and very well known topic. So here that aim of titration is to determine concentration of unknown solution with the help of known solution. So like that in titration, you know that in that burette titrant will be there, which having known concentration and known volume, and in beaker that unknown concentration of solution will be there, and drop by drop we will add, and then after at end point and equivalence point both amounts will be in equilibrium, and by indicator color will change, and through that we can understand yes, titration is done. So aim of titration is to determine or to understand that concentration of unknown solution. So here titrant will be where in burette, that will be known solution or a standard solution, and titrate in beaker unknown solution will be there. So there is two types of titrant which is there in burette. One is primary titrant. So for this no need to standardize before use. So that sample no need to standardize. Whatever the concentration there is the same, is not fluctuated. Whereas secondary titrant always before use we need to standardize, means its concentration we need to standardize it. So here are some few examples for primary and secondary titrant. Revise them properly. Sometime they are asking this one also. Now here types of titration, as last class I told you that 5 types of titration here we will study in this topic. So this one is, first one is acid base titration. Then after second we will discuss redox titration. After that double titration, then back titration, and last iodometric and idiometric titration. Remaining other two types of titration, that one titration we will study in ionic equilibrium, and one conductometric titration we will study in electrochemistry. So here that first acid base titration, so acid reacting with base, no need to balance, just you apply summation of all acid equivalent weight is equal to equivalence of that all bases. Means equivalence we can apply normality into volume, or molarity into volume into n factor, or n factor into number of moles. Next, redox titration, equivalence of summation of equivalence of all oxidizing agent is equal to summation of equivalence of all reducing agent. And on each topic we discuss sufficient problem also in classes, so that also you should parallelly revise. So here you can see in redox titration, first type of is that permanganate titration, MnO4 minus. So for this in acidic medium titration we will do, but acid HCl we cannot take and HNO3 we cannot take, because MnO4 plus 7 is there, so means it will reduce and it will oxidize other, so Cl minus will go to Cl2. So since here acid we are adding just for medium, but permanganate will titrate HCl also and HNO3 also, so its titration means its equivalence will be disturbed, means while applying law of equivalence that it will not be accurate value, so answers will be wrong. So that's why in permanganate titration we will not use HCl and HNO3 as a acidic medium, even will not use concentrated H2SO4, as I told that it will be a mild oxidizing agent. So just for medium dilute H2SO4 we will take, which will provide just medium for this permanganate titration, and indicators not required, so no indicator is required, because MnO4 minus 1 it is there at plus 7, so color will be pink or purple, is going to plus 2, so it is colorless. So here it is acting itself as a self indicator during titration. Second we are discussing here that dichromate titration in redox titration under. So dichromate plus 6 will go to in acidic medium plus 3. So it is acting as a, means it is getting reduced, right? plus 6 to plus 3. So other will oxidize, means it is acting as a oxidizing agent. Yes, here indicator we can use diphenylamine, and it will be colorless to blue at equivalent point. Clear? Next after that, back titration. So back titration, here what? That two equivalence titration we are doing. Let's suppose one is A and one is B. Both are titrated with each other. If A is in excess and B is limiting reagent, so B will be completely consumed, and then after remaining A titrated with another substance, that is C. So whatever the remaining A is there, that if it is reacting with C, so in that either C information will be given or A information will be given. So we can equate and we can calculate the needful asking point, whatever it is asking in that. Now coming to double titration. So in double titration, in beaker, these two substances will be there, and in burette, HCl will be there. So here you can see bicarbonate and carbonate is there. So when HCl, when we are pouring dip by dip, drop by drop, so first it will titrate with which one? So here you can see first reason is that carbonate having more charge density. So H plus first it will move to carbonate rather than bicarbonate. Another reason is that bicarbonate can lose H plus and can form CO3 minus 2, means behaving as a acid, or it can accept H plus and it can become H2CO3. So this type of nature of substances are called amphiprotic, whereas carbonate cannot lose H plus, means it can only behave as a base, means it can accept H plus, right? So that's why carbonate having more basic nature as compared to bicarbonate. Hence H plus, due to charge density and more basic nature, first it will titrate carbonate, then after bicarbonate. So here as it is titrating carbonate, so it is forming bicarbonate plus NaCl. In that indicator we will use phenolphthalein, and here that carbonate's N factor is 1. You can see it is removing only one H plus. So its N factor is 1. So equivalence of bicarbonate is equal to equivalence of HCl. Here you can take N factor 1, number of moles will be given, and here HCl number of moles will be given, N factor 1. Now after that, here you can see this bicarbonate is newly formed, and previously also in beaker bicarbonate is there. So now total this both number of moles you have to add. Let's suppose this is generated X and here it is Y, so both mole will be X plus Y, and for bicarbonate it is removing 1 H plus, so N factor is again 1, but number of moles will be X plus Y. Again we can apply law of equivalence. So equivalence of bicarbonate is equal to equivalence of HCl. Here indicator we will use basic methyl orange. Here indicator was acidic phenolphthalein. Clear? Now last titration, that is iodometric and ideometric titration. So generally it is used for estimation of iodine. So in that first I minus will oxidize into I2 by using any oxidizing agent such as KMnO4, K2Cr2O7, and then I2 will reduce by using hyposolution, any reducing agent, to I minus. So this is called iodometric titration and this is called ideometric titration. So here that I minus, if it is we are reacting with oxidizing agent, so it will form I2, which color is black or violet. And in that indicator we will use as a starch paper. So a starch and that I2 will adsorb on the starch paper, and its color also will be black or blue. And then after ideometric titration, so I2 reacting with reducing agent and forming I minus. So first step iodometric, second step is ideometric. So in that this I2 is insoluble in water, but due to presence of I minus, it is soluble in water and it became triiodate ion, which is brown in color. But for this titration, we need to have this two condition in our mind, that solution should not be basic. Otherwise, you know, in basic medium, dilute and cold, I minus I2 will go to I minus and I plus. And if it is hot and concentrated, I2 will go to I minus and I plus 5, right? So solution not should be basic, and solution not should be too acidic also. Otherwise, what will happen? This starch paper as an indicator which we are using for first step will decompose. So here are these some examples that how I minus and along with some oxidizing agent, understood, that oxidizing agent oxidizing I minus to I2, and they are getting reduced. So this is the first set of example of iodometric titration, and this one is ideometric titration, right, where I2 is going to I minus, hypo solution plus 2 going to 2.5, means this one is behaving as a reducing agent to reducing other and oxidizing itself, right? So here are some examples. Keep that all those in your mind. Now here first application of this titration. Whenever that we are titrating, so let's suppose A we are titrating with B, so B n factor is x, and same B is titrated with C. So here also its n factor, let's suppose its n factor is y. If both n factor, since B is same, amount wise it is same, now n factor wise also it is same. If it is n factor wise same, so suppose for first reaction we are applying law of equivalence. Equivalence of A is equal to equivalence of B, and equivalence of B is equal to equivalence of C. Now since n factor is same, so amount always will be same, number of mole. So number of moles into n factor, number of moles into n factor. So this equivalence is same, means we can say equivalence of A is equal to C. Clear? But if n factor x and y is not same, we cannot say equivalence of A is equal to C. Clear? Sir, n factor of y, this substance will be different. Yes, n factor for same element or substance will be different in different reaction. So if suppose n factor is different, so equivalent weight also will be different. So we cannot apply equivalence, means equivalence of B and B cannot be here nullified. So yes, so how to solve such type of question? So there you know that this B and this B in container it is same only, means their amount wise they are same, but their n factor could be different depending upon the reaction. So here application of this, what we have studied, that percent chlorine present in bleaching powder. So you know that here this is slackered lime reacting with Cl2, so forming calcium oxychloride. This is only bleaching powder and H2O. This bleaching powder if we'll heat, so Cl2 is releasing. So maximum theoretically how much chlorine is present in bleaching powder? So this mass is 71 divided by total mass of bleaching powder 127 into 100. So total in bleaching powder 56% theoretically it could be present. What? Cl2 gas. Now we are calculating actually how much it will be present depending upon the reaction or that questions given. So here you can see bleaching powder x gram when we are treating with acid, let's suppose acetic acid. So it will form Cl2 gas, and this Cl2 gas x gram forming let's suppose y gram. So according to this percentage of chlorine will be how much? Y divided by x into 100, correct? So from here Cl2 combining reacting with Ki, so I minus is going to I2, means this is what? Iodometric, and from I2 to I minus ideometric. Clear? So this is the application. So try to understand. Here Cl2 reacting with excess of Ki, so going to I minus is going to I2, and Cl2 is going to Cl minus 1, right? So here you can see that this I2 having n factor 2, because here minus 1, here 0. So overall oxidation number difference is 1 into 2, n factor is 2. And here I2 going to I minus, reacting with hypo solution going 2 to 2.5. So this I2 n factor is again 2 because it is 0 to minus 1 into atomicity 2. So this time you can see n factor is same, means this is already in excess. So equivalence of Cl2 is equal to equivalence of I2, and here equivalence of I2 is equal to equivalence of hypo solution, means now I can write equivalence of Cl2 is equal to equivalence of hypo solution. So equivalence of Cl2 is equal to equivalence of hypo solution. So equivalence of Cl2 how much? Equivalence of Cl2 will be whatever number of moles of Cl2 will be given into n factor. So n factor how much? Chlorine here it is going to minus 1. So chlorine as it is going to minus 1. So overall its n factor is 2. Clear? Overall its n. So yes, so here you can see chlorine having how much n factor. So chlorine as here it is Cl2, so 0 to minus 1. So overall n factor is 2, number of moles will be given. For hypo solution n factor you know 2.2 to 2.5, so 0.5 into 2. So n factor 1 into number of moles of hypo solution. So from here that given mass divided by molecular mass into 2 is equal to number of moles of hypo solution. So overall Y is equal to weight of chlorine, that is equal to 35.5 into hypo solution. So percentage chlorine 35.5 into number of moles of hypo solution divided by X. X is what? Mass of bleaching powder into 100. Clear? Here you can see number of moles of hypo solution is equal to molarity into volume or normality into volume also. Why? Because n factor is already 1. So molarity into n factor into volume is normality into volume, but n factor already for hypo solution is 1. So in both way we can calculate. Clear? Already in class we discussed some problem related to this. Now coming to very important percentage leveling of oleum. So percentage leveling of oleum is what? That from market whatever that you will purchase that H2SO4, in that free SO3 also will be there, and in that by adding water you will get next new H2SO4. Due to that how much leveling up happen for that H2SO4 is called percentage leveling of oleum. Definition wise we can define that mass of H2SO4 in 100 gram of oleum. In 100 gram of oleum, how much mass of H2SO4 is there? That is only called oleum. Understood? So here you can see, let's suppose 109 gram of oleum, means we can say 100 plus X percent of oleum. X is here representing amount of water, or we can write this one also 100 plus X gram of H2SO4. Means suppose for example if I am telling 100 plus X percent of oleum, means in that X gram of what is there? Water. So from X divided by 18 what I will get? Mole of water. That same mole analysis, that much mole of SO3. So if suppose this is also that much mole of SO3, so divided by its mass 80, I will get mass of SO3. Overall in 100 gram of oleum, suppose SO3 is 20 gram, so H2SO4 will be 80 gram. Now since whatever here mole, from this mole analysis new H2SO4 is formed. So here 80 gram plus whatever this one is formed, that is only called amount of H2SO4 in 100 gram of oleum. We discussed many examples back and forth. Now next, here you can see percentage minimum leveling will be how much? 100% of oleum, means X is here 0, means water is 0. Water is 0 means SO3 is also 0. So in bottle 100, in 100 gram of oleum, 100 gram of H2SO4 is there. That is the minimum leveling of oleum. Maximum leveling of oleum will be what? Let's suppose in that 100 plus, that here it is 100 plus X percent of oleum is there. Let's suppose that 100% oleum only there. X I am taking as a 100%. So if X is 100% oleum, 100% gel means water, so 100% will be that 100 gram of SO3 will be there. So 100 divided by 80. So how much it will be? Here 100 divided by 18. So 100 divided by 18, how much you will get? You will get mole as a mole you can calculate. So it will be 100 divided by 18, correct, huh? Or 100 divided by 80. So if you will divide 100 by 80, so clear? Once again I am telling, so here you can see that percentage maximum leveling. So percentage maximum leveling, so let's suppose in that 100 gram of SO3 only there, in 100 gram of oleum, 100 gram what is there? SO3. So 100 divided by 80. So 100 divided by 80 will be how much? 1.25. 100 divided by 80 will be 1.25 mole. So that much water will be there also. 1.25 mole of water into 18. So 1.25 into 18. How much it is coming? It is coming 22.5. So that's why 100 plus X is amount of water. So that is 22.5. So overall 122.5. So maximum and minimum percentage leveling of oleum. If it is minimum, then consider water as a 0 gram. And if it is minimum, then consider water as a 0 gram, 100 gram H2SO4. So if water is 0, so SO3 also will be 0. So overall in 100 gram of oleum, 100 gram of H2SO4 is there. In maximum 100 gram of oleum, you consider 100 gram as a SO3 only. So it will be 1.25 mole. So water will be also 1.25 mole. So overall by multiplying with 18, it will be 1.22.5 gram. So overall weight of oleum will be how much? 100 plus 22.5. X is amount of water I told. So this is the last topic here, volume strength of H2O2. So this is also concentration unit, like percent weight by weight, molarity, normality, like that. But this is only defined for one compound, that is H2O2. So definition of volume strength is 1 ml or 1 liter is producing, let's suppose, X liter of O2. So volume strength 1 liter, how much O2 is produced? X. So this is X and this V is the unit of volume strength. Suppose 2 mole of H2O2 breaking down and forming H2O and O2. So number of moles of O2 will be what? That 1 liter produce X liter. So X liter divided by at STP 22.7. So this is the number of moles given volume divided by 22.7. And here doing mole analysis. So number of moles of H2O2 divided by 2 is equal to number of moles of O2 divided by stoichiometric coefficient 1, that is X by 22.5. Since here it is 2 divided by 2, this stoichiometric coefficient. So this 2 is going up, 2 is going up. So overall it became 11.35. So number of moles of H2O2 came. So molarity is number of moles of H2O2 divided by volume is 1 liter. So overall from here X is volume strength only of H2O2. So X is equal to 11.35 into molarity or 5.675 into molarity. If it is given 22.4, accordingly also you can go on. So X is volume strength of H2O2. Relationship between molarity and volume strength of H2O2 is very important. Keep that in your mind. And here we completed completely all those segments. Thank you very much.